Hey folks, good morning, good evening. Let me introduce myself. My name is Nagesh Cherukuri. I'm the Principal Data Platform Architect in the Field CTO team. My specialization is in data apps. Today, I'll be covering modern data app architectures and best practices for building data apps with Snowflake. This is a 30-minute webinar. We'll have a Q&A after this session so that we can cover some of your questions once we have gone through this webinar. Thank you for taking time. So today's agenda is, let's cover some of the challenges faced by application builders today. And we'll cover Snowflake architecture, some of the key components in the architecture. Then we'll cover a few reference architectures with Snowflake. We'll conclude with some of the best practices, patterns, and where does Snowflake fit in and how to future-proof your applications. And then we'll conclude with Q&A. Hope that will be a good use of your 30 minutes. So let's start with the challenge. Today, if you look at many applications, application builders, they spend most of their time and energy and the cost in dollars go into undifferentiated heavy lifting. What I mean by that is, instead of focusing on the business opportunity and the business challenge, many of the application developers have to deal with scaling. As your consumer base grows, you need more resources to support them. And your demand varies from peaks and valleys. And as a team, you are required to over-provision resources, which hurts margins indirectly. As your org grows, the amount of data and data management also grows. This requires building complex data pipelines and maintaining them. Siloed data also leads to delayed time to insights, which will make your team members with specialized skills like knowledge of proprietary query languages. All of this impacts your productivity. You want to spend most of your time on the business problem rather than dealing with the data pipelines, and you need specialized skills to manage these resources. Lastly, there's immense operational burdens associated with building and running these data-intensive applications on traditional platforms. Teams spend most of their time in managing this infrastructure and monitoring the maintenance and availability of these applications. That's the biggest challenge in today's world. So before we go into the challenges, what exactly are data apps? What are the examples of data apps? Any customer or employee-facing applications which process large volumes of data and fast-changing data, those applications are we call data apps. And some of the examples of data apps are payment applications that require analytics on customer spending history, or next-gen CRM systems that needs to search petabytes of data or gigabytes of data and fast. And the third one example, which is very relevant in the industry, is security analytics, the SIEM systems, which needs to detect and respond to threats in near real time. These are some of the examples which deal with big data and which needs a system which can address these data apps. Continuing on the challenges with traditional architecture, if you look at a three-tier application, on the right side, you have web applications, you have mobile applications interacting with a middle tier, which might be made up of REST API or a GraphQL API, which in turn talks to your data tier, which might be a combination of OLTP and OLAP systems. And on the right-hand side, you see you have to serve different business users like your BI business analysts, a BI team, or your ad hoc analytics team. And most recently, a lot of machine learning applications, machine learning use cases are all served from this data tier. But if you look at this, there are a wide variety of problems or challenges, what we call. One is scalability, which comes to my mind, is if you have to scale this application to serve different users and address peaks and valleys, you have to over provision today. That leads to costly scaling. And the next one is agility. You need to adhere to the changes based on your varied demands. Your concurrency limits might change with time, and your infrastructure have to be elastic to change to that demand. Today, that's pretty difficult to make that changes on the infrastructure in real time or near real time. The third one I want to cover is governance and security. Every application today have to adhere to some of the regulatory requirements based on what vertical, what industry you are in. And ability to ensure data security is a big challenge. Integration, the integration challenges with various tools. There's a myriad of tools out there which you have to integrate to. And when you integrate with all those tools, your complexity grows. You have to adhere and address those complex operations. The final one I wanted to call out is today's applications, your data sets which are produced or sourced or consumed might have to be shared with different business units within the organization, or sometimes with the third parties and partners and vendors. And today's inability to effectively collaborate with different teams and stakeholders within and outside the organization securely is a big challenge. These are some of the challenges which we see in the industry when you talk about a traditional architecture. Now let's look at, when you try to address these challenges, you want to pick a cloud data platform which can scale, which can address your real-time peaks and valleys, varied demands, and which should address your security concerns, which we talked about, to address your regulatory requirements. And you don't want to spend a lot of time managing this infrastructure. And you wanted to make sure it addresses unlimited scale and performance. So if you are going to pick a data platform, you want to have at least these 4 qualities. You want to have one platform, one copy of data. You want to have secured access to these data sets, no silos, and it delivers unlimited scale and performance. And it should be delivered as a service so that you can focus on querying and not managing infrastructure. These are few of the qualities which you want to see in your data platform. So come Snowflake architecture, the Snowflake cloud data platform is built ground up to address those concerns. It is made up of 3 layers, 3 critical layers. One is the optimized storage, which addresses all your data storage requirements. The middle layer is the elastic performance engine. This architectural layer addresses your elastic scaling of compute. And the third one, the top layer, is the intelligent infrastructure, which manages both compute and storage and ensures that this one platform addresses all your requirements without resulting in any trade-offs. This drastically simplifies things for you customers to accelerate your engineering impact. That's how Snowflake 3 unique architectural layers help you build a cloud data platform or adopt a platform which addresses those challenges. Whenever you are on your journey with data, this one platform makes it possible to address most of those challenges, if not all. This unique architecture lets you break down silos to bring all the wide range of data sets together and support many different workloads shown above, like data engineering, data science, data applications, cybersecurity, and collaboration. In today's webinar, we'll cover few of the reference architectures and few reference customers who adopted the platform and gained this advantage of one platform. This platform gives you the necessary capabilities to deliver on your most critical objectives. So how do we do that? How do we deliver a high-performance app at scale on Snowflake? So we talked about those 3 tiers: app tier, the application tier, the middle tier, and the data tier. Let's dive into what makes Snowflake uniquely set up to help you scale your app seamlessly. Snowflake's multi-cluster shared data architecture spins up compute clusters, which you see those gear boxes on the top. Um, this can result in supporting multiple business units, unlimited number of concurrent users without contention or performance degradation, allowing you to deliver a superior performance no matter what the demand is. First, looking at your internal workloads, you could have routine data load that is daily, monthly, quarterly. But since the data is rather predictable and manageable, you can allocate a extra small compute cluster on the far left for those requirements. If your data science team, you have a data science team, and the data science team is asking for access to the data, we want to right size the compute for them for each individual workload. In this case, you see that we assigned a medium compute to a data science. That's an isolated workload. We are providing a isolated compute for that particular team. And for marketing here, we provided a small cluster, small compute cluster, what we call small warehouse. That's how we isolate compute for each of those workloads. And if you see, we can provide a multi-cluster warehouse for people. If you have a requirement where there are many teams which require to be shared, we can provide a multi-cluster warehouse so that we can scale out to respond to the user demand without contention or performance degradation. We can scale up as well. If you see in the previous, the cluster was medium. We can scale the cluster up to large to ensure performance of larger or more complex queries, so that we can scale to demand, scale up as well as scale out. As we discussed earlier, we can allocate isolated resources. Here we are allocating extra large resources to meet that individual team's demands by designating dedicated warehouse. So we have assigned a dedicated extra large warehouse to a team which has the demand to access that data, which might be large complex queries. And again, it's consumption-based pricing. With Snowflake, you get price based on the warehouse you picked. In this case, you can avoid your over-provisioning and overpaying as you pay per server and per second. You can reduce or increase your size of the cluster from medium to large or large to small. And you pay based on your usage. And it's per second billing and per server. Moving forward, I wanted to cover this slide. This is the middle tier, which we talked about, middle unique architectural layer, the elastic performance engine. We can have one engine for every workload, which simplifies your architecture. We can go with different compute for different workloads. This eliminates, you don't need to rely on one compute. It is dedicated compute for dedicated workloads. With this unique architecture, a single engine can support every workload. This eliminates needs to bring in multiple different engines for processing data, analyzing it, and then trying to stitch them together. We see, we see customers using multiple engines, but it brings complexity into their architecture as they have to process data in one engine, move it to other engine. It brings security, regulatory concerns, and stitching them together is a pain. But with Snowflake, you have all in one platform. You get blazing performance for large complex pipelines. You can do feature engineering, interactive applications, analytic dashboards, and many more. Not just that, without need to worry, you can do you don't need to worry about resource contention or tuning, as we do it for you under the hood. This can elastically scale to support any number of users, jobs, or data size with multi-cluster resource allocation. It means you'll have reliable performance every time. And whether your team is comfortable with SQL or even if they prefer working with other languages like Scala, Java, Python, you see that they can take advantage of the same engine because Snowflake supports Scala, Java, Python, JavaScript apart from SQL. So getting into what we talked about, a simple architecture with Snowflake, let's take an example. Here, Snowflake scales the existing environment as you see in a much simpler and cost-effective way. It gives consistent performance. The cost savings can be achieved through this elastic compute. Snowflake basically stores data at low prices and supports all analytical workloads. So you don't run into proliferation of database technologies. You ingest your data continuously with no downtime or performance impact. So the apps can deliver fresh data to your customers. If you see the picture on the right, you have your application talking to the middle tier, like what we have seen earlier in the traditional architecture. The data is coming, the low latency data is coming from your OLTP NoSQL engines. The data is fed into the Snowflake platform via Snowpipe. And the Snowflake platform provides you instant scalability, the workload isolation, and support that fast analytical queries you can directly access through a SQL API or connectors and drivers from your app directly to Snowflake by connecting directly to Snowflake. And you can see that we have a workload isolation where business analytics can have their own virtual warehouse and machine learning can have their own virtual warehouse. So we provide dedicated warehouses to dedicated workloads. So let's look at a couple of reference architectures. I picked a few handful of them to walk you through this. So the first one is this embedded analytics. This is the most proliferate use case where we see many of our customers, where they have a application which is interacting with their OLTP engine. There might be a NoSQL, there might be SQL Server Postgres, which are required for low latency applications, but they also need data from an analytical platform like Snowflake, which needs to be provided for aggregate queries, grouping, filtering on a large data sets. All the data is fed into Snowflake, and Snowflake automatically scales, provides that instant scalability. And Snowflake is on all three clouds, AWS, Azure, and GCP. And we provide that fast analytical querying capability where you can directly connect to Snowflake via connectors and drivers, or you can directly embed your application, a business analytics application like Tableau, into your app. And that app can communicate with API tier, and that API tier can in turn communicate with Snowflake. So with this architecture in Snowflake, you are getting an easy management. You are not really tuning your infrastructure. Instead, you pick your size of compute, small, medium, large, a t-shirt size. You dedicate a warehouse, and we scale that instantly based on your demand. And we also support these fast analytical queries through our auto clustering, search optimization, many other features which provide you that ability to search the platform in a pretty scalable fashion. So this is a most prominent use case where we see customers build heavy applications. Again, this is a common architectural pattern. This is not just the only way to do it, but many a times we see customers adopting this architecture, one platform, so that they can ingest the data, do processing on that large data sets, and make the data available to your business analytics, as well as the data applications which are embedded, which are embedded with the platform. So the next one I wanted to cover is the security analytics reference architecture. This is one of the most common architectures we see across security conscious, security data lake customers. As you can see, the way to read this architecture is from left to right. You see that your application is ingesting logs into your log collection systems, and your log collection systems in turn feeds that data into a streaming systems like Kafka or Kinesis or Event Hub. And from there, you can feed the data directly into Snowflake via Snowpipe, whether in a streaming or batch fashion. Or the data can be fed into an object storage like S3 or blob storage or Google Cloud Storage. And from there, the data can be batched and fed through Snowpipe into cost-effective log storage in Snowflake. And from there, we have streams and tasks which analyze that incoming data, process that data, and make the data available to messaging services or monitoring dashboards or ad hoc querying analysis, or even for any applications, machine learning applications, which can run processing on that, identify threats in near real time, and feed it out to messaging service, which will in turn can send it to your email or SMS. We see many customers adopt this architecture, and I want to provide some reference customers like Securonics, Hunters, Panthers. These are some companies, some organizations which work on security data lake, and they adopted Snowflake and they run Snowflake underneath their covers to power their customers. In the previous slide, I talked about embedded analytics, and few of the customers like IKEA, Springox Capital adopted this architecture, a variation of this architecture, to embed their data analytics platform. The last use case I would like to cover, a reference architecture for machine learning. This is one of the more recent architectures we have seen customers adopt, their data science platforms powered by Snowflake, where if you see from left to right here, your applications are again streaming the data through a streaming service like Kafka into Snowflake. And Snowflake does the data refinement curation using streams and tasks. You can even query the data in the object storage using external tables, where the data can be left in place in object storage or your data lake, and Snowflake can query the data. And using UDFs, we can build models, and that model can reside within Snowflake, and you can access from your machine learning platform. You can do inference in Python UDFs. You can also have Snowpark, one of the feature in Snowflake, which basically helps you do inference on those models. Once data is available for querying in Snowflake, the tasks can schedule stored procedures to perform required transformations. Data scientists can process training data directly inside Snowflake with flexible instance scalability to support feature engineering and experimentation. Snowpark developer platform, which we talked about earlier, provides API for querying and processing data in a data pipeline. And trained ML models can be run within Snowflake using, we talked about languages like Python, Scala, and Java UDFs, or externally with another ML platform leveraging external functions. Using the data stored in Snowflake, data scientists train models with ML platforms, external platforms like DataIQ, DataRobot. We called out a few of these here, but any ML platform can work with Snowflake trained models. Once trained, the model artifacts are deployed on the training platforms to support predictions. Training can also be done within Snowflake, leveraging Snowpark and Snowpark optimized warehouses. Snowpark optimized warehouses are extra large warehouses which supports feature engineering, which are basically placeholders for large memory required use cases. The application performs predictions using these models in real time or scheduled batch predictions using the deployed models. For batch predictions, data is read from an input table in Snowflake, and the results are stored in an output table where they're available for the application consumption. So many of our customers adopted this common architectural pattern. Few of the customers I have seen use this is Anvilogic, Innovid, and so forth are some of the customers who adopted and utilized the data science, ML pipeline, and orchestration within Snowflake platform. I just wanted to cover those few reference architectures to give you some idea of how Snowflake can help with your analytical, with your data science, with your security data lake use cases. on extra large data sets. Now let's talk about where does Snowflake fit in application use cases. Snowflake is optimized for more complicated analytical queries on large data sets. As query complexity goes up on traditional, OLTP databases, users will be impacted and your resources will struggle. They'll be inefficiently used due to inability to distribute queries. Snowflake, with its separation of compute and storage, offers more options. Data never requires sharding like what you have to do in regular OLTP systems. So you can add more compute, so queries can always span the data that is needed. Single cluster warehouses, you can see, supports 1 to 10 concurrency, and multi-cluster warehouses support tens to hundreds of users, 10 to hundreds of concurrent users or synchronous queries. Snowflake can accommodate single-digit seconds query responses depending on the compute size you allocate and the complexity of the query and how much data you can cache. When going above 100 concurrency, additional work needs to be done to handle the load, like splitting workloads vertically into many multi-cluster warehouses that will add horizontal concurrency to. At concurrency above 100 and latencies need sub-second, Snowflake warehouses can be used to run queries, and then the results can be then stored back in OLTP or NoSQL systems or cache to provide that low latencies. So this is where, when we look at the data app patterns, this is where Snowflake sweet spot is. Now let's talk about what are the capabilities of Snowflake platform as a whole. The ease of development. We have a robust collection of connectors and drivers, which I'll cover in the next slide. We have native SQL capabilities for semi-structured data sets, geospatial. We separate storage and compute, as we have seen earlier. We can store large volumes of data in a cost-effective fashion. We can scale up the compute with dedicated clusters for isolated workloads. We have adaptive caching where we cache metadata and data and query results. We have hot and cold layers for cost efficiency and performance. One platform provides simplified management, provides extensibility with Snowpark, stored procedures, UDFs, and external functions. We provide extensibility to the platform. Cross-region cloud replication for high availability across clouds and low latency to customers. Data sharing is one feature which is pretty widely used in collaboration. You can easily share and enrich data to your partners, vendors in near real time. Security is paramount. All data in the platform is encrypted, compressed, and access can be provided using RBAC. So as I talked about earlier, we have a wide plethora of native Snowflake connectors. Use a native Snowflake connector. We have many language support like .NET, Node, Spark. Designed specifically for that language, best practices are built in that connectors. Connection pooling, security is built in throughout the platform, throughout that connectors. Also, we have many partners who are supporting us in building these connectors. More prominent ones I have seen is CData, .NET connector, which is widely used. But you always have native connectors here. Some of the best practices I try to cover here is, as we talked about, isolate your workloads into separate warehouses to get the maximum and for cost savings and affordability. And you scale out workloads automatically with multi-cluster warehouses. So we can go up and down as the demand varies. We can scale out the workloads with multi-cluster warehouses and use RBAC and organizations to control access and reduce risk. And leverage clustering wherever possible, the materialized views clustering and search optimization for query performance. Those three, the auto clustering, materialized views, and search optimization service helps you with your query performance. The next one is pairing Snowflake with an OLTP and NoSQL engine for both analytical and operational capabilities is a common pattern we saw and a best practices to address your low latency requirements as well as to address your long running queries, complex queries on large data sets. use change data capture to sync changes from other databases. We are not asking you to, move all your OLTP data onto Snowflake platform. Wherever you need analytics, you sync your changes to Snowflake. Replicate for 3 nines availability, and use an event bus to stream or batch the data into Snowflake using Snowpipe. These are some of the best practices we have seen who adopted Snowflake as their common data platform or as their cloud data platform. Thank you. I would like to take questions, but thanks for spending your 30 minutes with me. Hope it's useful, and we'll stay on for questions. Thank you.